All right. So when we talk about moment is basically a product of force and distance, right? So when you take the force and you take the distance and you multiply them with each other, you are able to calculate moment. What exactly is moment? So moment is uh, when you are, for example, opening your door, right? So if you apply a force close to the hinge, you will need a lot of force to open it up. But if you apply the force far away, usually where the doorknob is, it's much, much easier. Same concept is if you are unscrewing a nut, if you're opening up a bolt or a nut. If you try to do it with your hand, right? So the rotational force that you need is really, really high. But if you use a wrench, what will happen? That the force you need is lesser. That is because the distance from the pivot has increased. So then you take your force and you multiply it by the distance from the pivot, you can produce moment, which makes it easy to rotate things or easy to actually um basically rotate things. So now force into distance is the formula for it. Now I don't know if this is something you have ever thought about or not, but the question that might come in your head is that when we talk about work done, okay, work done is also force into distance. Turning effect of moment is also force into distance. So what is the difference between work done and turning effect of moment? So when we talk about our distance, in turning effect of moment, we always have perpendicular distance. So this will produce a moment. Now the difference between moment and work done, even though they have the same formula, is the distance that we take into account, right? Turning effect of moment involves perpendicular distance. So the force and the distance have to be at 90 degrees to each other. In work done, the force and the distance are in the same direction. So that's the major difference. Even though they have the same formula, but in work done, the force and the distance are in the same direction. In moment, the force and the distance are perpendicular to each other. So moment, the unit of moment is always going to be Newton meters. Now, whenever you're solving your past paper questions, you might notice a few interesting things about it. You often will see that the examiners will say that you have a system that is in equilibrium. Okay. So when we talk about equilibrium, what exactly do we mean by equilibrium? Okay. For any system to be in equilibrium, there are two requirements. Number one, there needs to be no resultant moment, no overall moment, no net moment. So no, there should be no net moment. There should be no resultant force. So there are two criterias. There needs to be there needs to be no resultant moment, and there needs to be no resultant force that is acting on the system. That is the requirement for the system to be considered in equilibrium, right? So what do we mean by no resultant moment? To understand what we mean by no resultant moment, let's take a look at a small question. 1 second, hold on. So for there to be no resultant moment, the clockwise moment has to be equal to anti-clockwise moment, right? So how, for example, let's say we have this question in front of us, okay? And we have to figure out if this is in equilibrium or not. Like that's what the examiners have given you, that this is that you have this system. Do you think that the system is in equilibrium? Yes or no?
I think
So,
it's
yeah,
not in equilibrium, right?
let's see. So we are going to check first of all the clockwise moment and anti-clockwise moment. We check both. How do you check for clockwise and anti-clockwise moment? Okay. So first thing is you have two forces that are acting downwards. We have to figure out which force is clockwise and which force is anti-clockwise. The way you figure it out, Hajra, is follow the arrow down and then turn towards the pivot. Okay. Follow the arrow, turn towards the pivot. So the force is going down. So I move my arrow down and then turn towards the pivot. So this is anti-clockwise. And this one will be follow the arrow down, turn towards the pivot. It will be clockwise. Okay. So clockwise, we are going to use the formula force into distance. Okay. Clockwise, the force is 300 newtons and the distance from the pivot is 1 meters. So clockwise moment is 300. On the other side, we have 200. 200 multiplied by 1.5, force into distance. So again, we get 300. So clockwise and anti-clockwise are coming out equal to each other. Okay, so this is, at least the first option is correct. There is no net or overall moment. Then let's take a look at the forces. There is a force acting downwards of 200 and another force acting downwards of 300. So 200 plus 300 gives us 500. That means there is a total force acting downwards of 500. Now you might be looking at this and you might be wondering, okay, miss, but then you said that there needs to be no resultant moment. So there is no resultant moment. But you also said there should be no resultant force. But over here, we do have a resultant force. It's 500 newtons acting downwards. But what you don't realize is that there is an upward force that the examiners will never show you. And that is contact force at the pivot. Okay, the contact force at the pivot is never shown to you by the examiners because it doesn't produce any moment. But you should, from your theoretical knowledge, remember that at the pivot there will be a contact force acting upwards of 500 newtons. So there is no overall momentum and there is, sorry, no momentum, no overall moment, and there is no overall force. So this system is going to be balanced. Let's take a look at another question. So we have a uniform wooden meter ruler that has a mass of 0.12 kg. A pivot at a 40 centimeter mark supports the rules. When a brass made weight is placed at 20 centimeter mark, the ruler balances. Calculate the mass of the brass weight. Okay. So we are going to start by first finding, this is the pivot, clockwise and anti-clockwise. Follow the arrow and turn towards the pivot. So the brass, this is the brass weight. It is producing what? It is producing anti-clockwise. This is the weight of the scale. 0.12. I've written 1.2, but it's 0.12. So it is going to go downwards and turn towards the pivot. So this is clockwise. Okay. So first we calculate the clockwise movement. The clockwise moment is going to be force into distance. And we need distance from the pivot. Okay. So now the thing is, Hajra, that the distance from the pivot is not given to us, right? We will have to figure it out ourselves. So 0.12 is the mass of the meter ruler. Now, one thing that you have to always remember, whenever you have a uniform object, you, whenever you have a uniform object, the mass always acts at the center. Always. Okay. So that means this is the mass of the scale 0.12. So where is it acting? It is acting at the center. So that means the distance of the mass 0.12 is 50 centimeter. Okay. Now the pivot is at 40 centimeter. So if I want to find this, the distance of the mass and the pivot, I will do 50 minus 40 and I will get 10 centimeter. Okay. So I will do force into distance. Force is 0.12 and distance is 10. That is how I will calculate the clockwise moment. Making sense how I'm getting the distance from the pivot?
Can you just repeat how you got 50
Yes.
centimeters?
50 centimeter I am getting because this is a uniform meter rule. And this is the mass of the meter rule 0.12. Okay. So
Okay.
remember this, for any uniform object, the weight or the mass is always at the center. Okay. So any uniform object, whatever uniform object you want to take, remember this, that the mass is always at the center of the object. So this is a meter rule, which is a total of 100 centimeter. So the center of it will be 50 centimeter. That's how I got the value. Okay.
Okay.
So just the center of the ruler, that's it. Okay, now we need to get the anti-clockwise movement. Okay. Again, the anti-clockwise movement, we have the force is unknown. The force is the weight of the brass. Again, we need the distance from the pivot, right? That's what we need to find out. What is the distance from the pivot? So we know that this is 40 centimeter. From the corner to the pivot is 40 centimeter. The brass is 20 centimeter. So we can, this is total is 40 centimeter. This distance is 20 centimeter. So if I would find the distance to the pivot, I will do 40 minus 20, right? Which will give me 20 centimeter. So the distance to the pivot is going to be 20 centimeter. So the total distance over here is going to be 40 centimeter to the pivot. The brass weight, the distance of the brass from the edge is 20 centimeter given in the question. So my advice is, in these questions, always draw these arrows. They'll make your calculations easier. So 20, so we need this distance. So 40 minus 20 gives us 20 centimeter. That is the distance to the pivot. So anti-clockwise movement is going to be weight of the brass multiplied by 20 centimeter. 1 second, Haja, I need to get my charger.
Okay.
Right. So, so we're going to do 40 minus 20. So for the anti-clockwise, it will be weight of the brass multiplied by the distance to the pivot. The distance to the pivot is 20 centimeter. So weight multiplied by 20 centimeter. So we are going to get 20W, right? We have to basically find the weight. So we know that clockwise moment is equals to anti-clockwise moment. Clockwise moment we had calculated as 12 and anti-clockwise is 20W. So simply divide the two of them and you get the weight as 0.6. Okay, so this is how you're going to do your clockwise, anti-clockwise calculations. This topic basically is a lot of just past paper practice. That's it. You just need to do a lot of past paper practice, and that is the main thing. That's the main thing that you have to do. So, making sense, Hajra, how we solved the question? Any confusion in this particular question?
No.
Oh. Now, when we talk about the center of gravity, so you probably do know this because this is a simple concept. But I told you that the center of gravity is usually as at the center, right? That's what I just told you. I told you that the mass always acts at the center. So mass, center of gravity is the point on which the weight of the body acts. Okay. The point on which the weight of the body acts is your center of gravity. So what is going to happen that the for uniform objects, the center of gravity is always in the middle, right? So for the meter ruler, I said it will be right in the center. So 50 centimeter. So any uniform object, the center of gravity will be right in the center. But what do you do if you have a non-uniform object, like an object that is not uniform? For example, we have a really weird shape over here. So how can we figure out the center of gravity of this shape? So it's really simple. What you do is you take a pin and to the pin you attach a thread and to the thread you attach a mass. Then you place the pin anywhere on the edge of the shape. Then the thread will hang down. As the thread hangs down, you will use a pencil and make a mark following the shape of the thread. Okay. Then you will turn the shape. Again, place your pin at the edge and again follow the thread and make a mark with the pencil. Again, turn it around to a different angle. Again, insert the pin with the thread and mark where the thread is going. And you do this multiple times. Towards the end, you will have your pencil lines that will all be intersecting or joining at one point. That point will be the center of gravity. Then, when we talk about objects with, remember this, objects that have low center of gravity are more stable. That's why a lot of your low cars are more stable, and those really big cars or your tall trucks, your buses, they're less stable. The reason for that is because the taller it is, the higher the center of gravity is. So objects that have low center of gravity are more stable. And objects that have a wider base, they are more stable. Okay. For example, if we take a look at this example over here, so you can see that the center of gravity is at the same height. But when the object tips, right, when the object tips, if the base is small, so the center of gravity quickly moves out of the base and the object will fall down. On the other hand, if the base is wide, so even if the object tips over, the center of gravity is still within the base. So the object will simply fall back to its normal position, right? So that is basically all there is to turning effect of moment. So if this is all clear and you don't have any questions, let's take a look at some questions on the topic. Okay, take a look at this. A weightless beam is balanced on a pivot as shown. Forces P, Q, and R act on the beam. Which equation is correct?
I think it would be C or D, but I'm not sure which one.
Okay, let's see. So we have got P and R, and we also have Q. Okay. First thing is first, Hajra, you have to identify which is clockwise and which is anti-clockwise. So let's start with P. Go down and turn towards the pivot. So P is anti-clockwise. Q. Go up and turn towards the pivot. So Q will be clockwise, I think. R. Go down, turn towards the pivot. So R is also clockwise. So that means that in anti-clockwise, we have P, and in clockwise, we have Q and R. Now, we will do force into distance. So anti-clockwise is P into distance. So the distance of P from the pivot is this thing. So P multiplied by D. Clockwise is going to be Q. So Q multiplied by distance from the pivot. Distance from the pivot is D. Plus R is also anti-clockwise. So we added in the clockwise one. So the distance from the pivot is A. So R multiplied by A. So anti-clockwise is equal to your clockwise. So anti-clockwise is P into D. Okay. So that means answer is either C or D. Now we have to choose C or D. So P into D is equals to Q into D plus R into A. So this option is not there. Now option A is saying P into D plus Q into D. That is not correct. Option D is saying P into D minus Q into D. That is possible if we move this to the other side of the equation. So P into D minus Q into P is equals to R into A. So the correct answer is option D, right? Making sense?
Yes.
Okay, let me share another question. Okay, take a look at this. The diagram shows uniform beam pivoted at its center. The student applies two force F1 and F2. Which row is correct?
Would this be the last one?
One second. Let's see. Okay, so you're saying the last one, right? F2 into D4. This will be clockwise. Follow the arrow down, turns towards the pivot. Yes, okay. and F1 into T3. Yes, you are correct. Okay, take a look at this
This one would also be D, right? The last one.
Yes, L the last one, correct. Okay, define moment of force and describe the effect that it measures.
So the moment of a force is the turning effect of a force, like from a
Yes.
fixed level.
Yes, force into perpendicular distance from the pivot. Yes.
And the moment of force, it'll determine like how a force can cause the object to rotate.
Rotate or yeah, or turn. Yes. Okay, take a look at this one. Explain what is meant by, you can read the question and then explain what is meant by center of gravity.
Uh, the center of gravity is the point on which the weight of a body acts.
Correct. The weight of the block is this much. Calculate the moment of the weight of the block around corner X.
I'm not sure how to solve this one. Like, how would you solve it?
Just use the formula force into distance, right? That's it. You just have to calculate using turning effect of moment. The force is acting downwards like this. So that is the weight of the block. And then you just need the perpendicular distance to the pivot. So the pivot is x. So you just need the perpendicular distance to x and use the formula. That's it.
I got my answer as 4.42 into 10 to the power 7.
Are you dividing 3.4 by 2? Because 3.4 is the total width of the thing, right? You just need the distance from the center to the pivot.
I did 1.3 into 10 to the power 7 into 3.4.
Yeah, so you need to divide 3.4 by 2 because the distance from the center to the pivot is half of this.
Yeah.
See, that's why I drew the arrow for you. You can see that my arrow is from the center to the pivot. So this is the entire distance.
So I should just divide it by 2, right?
Yes. So
Okay.
what would you get?
So it would be 2.21 into 10 to the power 7 Newton meters.
Yeah, that's fine. Okay, now let's see. They're saying state two different conditions that apply when an object is in equilibrium.
One is that the anti-clockwise moment should equal to the clockwise moment,
Yes,
and there should be no resultant force.
that's correct. All right. Okay, Haja, we'll go ahead and stop it over here for today.
Okay.
And